List of achievements of Evina, I was greatly surprised, shocked that she is a really leader of astrochemistry in the world. She was a pioneer in astrochemistry some years ago, but now she is a real leader in this branch of science. She is well known over the world, and now she's acting as a president of International Astronomical Union, that's so leader of astronomy. I would like to give the floor to Evina, please. We will travel through universe now.
Okay. Thank you very much, Boris. Good morning, everybody. It's wonderful to be here in St. Petersburg and in Russia. This lecture is not going to be in Russian, but I hope that you all can all follow the English and also the slides. What I'm going to do, actually, in the next 40 minutes is take you through a tour of the universe. The first part will be to discuss where the elements that make actually also up us, where they do come from. There's a very nice poster there in the back, Space, it's called. So in the first half of my talk, I'm going to touch on that and explain a little bit what is in that poster. In the second part of the talk, I'm then going to delve into astrochemistry, namely what can we do with those elements in space, what kind of molecules can we actually form from that. Now, I'm standing here as an astronomer, as an astrochemist, but I'm actually also the president of the International Astronomical Union these 3 years. And as you all know, this is the year of the International Year of the Periodic Table of the chemical elements. But at the same time, we are also celebrating 100 years of the International Astronomical Union. And of course, the two go hand in hand because we study the formation of those elements and what they do in space. And so there's a clear link here with Mendeleyev's 150-year celebration. And I'll come back to that at the very end of my talk. Now, before I dive into the science, it is good to take sort of a little bit of a broader perspective. You've heard this morning talks about applications of elements in materials and material sciences and in the industry. But let's take sort of the bigger picture and the bigger question. Namely, where do we come from? What is our place in the universe? Are we alone? And these are questions that are not just of interest to scientists, but that actually fascinate humankind more generally. And you see that reflected, for example, in arts. Dutch painter Vincent van Gogh, he just had to paint the Starry Night. And you see that beautifully here with the Big Dipper. But you also can go to other parts of the world, for example, in Australia, the Aboriginals, and they also are fascinated by the beautiful Milky Way that they have above them, and they paint here the Milky Way dreaming, where you see the Pleiades with Orion on top. Now, where do we come from? Certainly, the elements that we have in our body were made in the Big Bang that created our universe, and then also subsequently through nuclear burning in various stars. And in fact, when you look at the periodic table in this way, you see only there in the bottom the man-made elements that you heard about yesterday during the plenary lectures. But the rest of the elements are made either in the Big Bang, such as hydrogen and helium, or they are made in stars. Some of them through nuclear fusion in small stars, some of them through nuclear fusion in large stars, big stars, and then also supernovae explosions. There we get to temperatures that we can really go up to some of the highest elements. So let's take a tour and just see briefly from where the elements actually come from. So hydrogen and helium were actually made in the very beginning of the universe, in the first minutes, basically. And you can go back to reading some of your favorite novels and books about that. Of course, Stephen Hawking's A Brief History of Time. The First 3 Minutes from Steven Weinberg. They tell the story of that time. I also like this quote from Richard Feynman. I, a universe of atoms, an atom in the universe. Just to, again, give you that perspective. But here you see it in sort of a timeline, the Big Bang that happened some 13.7 billion years ago. Initially incredibly hot, that's when you had the sort of quark soup, but then when the expansion of the universe, the materials started to cool, you get the expansion, and you get then to sort of the first seconds and the first minutes when you actually have the conditions on which you can form protons and neutrons. So basically, because of reactions that can still take place in those first minutes, you can transform some of the neutrons to protons, and you end up with a ratio of protons to neutrons of about 6 to 1. Now, once you have protons and neutrons, then you can actually have them nuclear fusion with them, and that leads then to deuterium, of course, and then if you have 2 deuteriums, you can also form helium-3 with a neutron. So those are the main elements that you actually make in the early universe in the first 3 minutes of the universe. You can go on a little bit, you can make a tiny bit of helium-4, but it's really mostly helium-3 that is made. And in fact, when you look sort of at those first few minutes that you see there on the top line, unfortunately we cannot point here at the screen, but if you look at the timeline on the top, then you see that in the first few minutes you make those protons, you make hydrogen, you make deuterium, you make triplet helium-3, but then basically the expansion of the universe is already such, it has cooled enough that those reactions can no longer occur. And so these abundances are then frozen in. And if there had not been any fluctuations in the early universe, that would have been it. That would have been our universe, just consisting of hydrogen, deuterium, and helium-3, with a tiny bit of some of the other elements interspersed. Fortunately, there were some structures implanted on the universe at the very early times, and they led to the fact that we are not sort of in this big freeze-out forever, but that they can be amplified and that they can lead to the first generation of stars and galaxies that then eventually lead to the universe that we have today, the modern universe. And we can see those tiny fluctuations beautifully, such as here in the data from satellites that looked at the cosmology. The COBE satellite first that showed that the background radiation from the Big Bang now has a temperature of 2.73 Kelvin. And then subsequently WMAP and the Planck satellites mapped in exquisite detail sort of the deviations, the tiny, tiny little deviations at the level of, say, 10⁻⁵ with respect to that temperature over the scale of the universe. And that's what you see here. And it's these tiny little fluctuations that are the seeds for future structures. That's then the regions that, the overdensities that then can eventually collapse to form the first stars and the first galaxies. So, and that has been simulated also in hydrodynamic simulations. This is just one time frame from one of these cosmological simulations. You just put in all the known forces and you let the universe evolve in your computer, and out comes these beautiful images that you see also over here. And it's really sort of in the intersections of several of these filaments. You see it's a very filamentary structure in the intersection of these filaments where we form the stars and the galaxies. We now know also that our universe is not just consisting of matter, of atoms and molecules. In fact, the bulk of it is actually this mysterious dark matter and dark energy that I will not go further into, but that also plays a large role in the evolution of these structures. So, The first billion years, we started from this primordial soup in which we made hydrogen and helium. We had the giant hydrogen clouds when the universe was cool enough to recombine the protons to form neutral hydrogen. And then the first structures started to form. We get the first stars, we get the formation of the galaxies, and then that's what we have now today. And of course, as soon as we have the first stars, then in the interior of those stars, it gets hot enough, say 10 million degrees, for nuclear fusion to occur. And that is when we start to produce several of these elements that we need. The first stars were probably very big, and they produced certain elements, and then the subsequent stars were smaller, and they produced other sets of elements. And this is actually what you will hear, those of you who are going to attend actually the symposium on the periodic tables through space and time. You will get to hear much more about this whole sequence and the formation here of these elements. Now, what do we actually have today? In what sort of proportions were these elements formed? Now, one way to see that is to look in detail at the sun. The solar spectrum that we can analyze in detail. We have very high signal to noise of that. Another way is to get some material. And of course, ideally, we would like to fly into space and take a little bit of material there and analyze it, bring it back to Earth and analyze it in great detail. But that is not yet what we can do. Instead, what we do is actually analyze the meteorites that fall on Earth and look in detail at their composition. And it turns out that the composition of those meteorites is very, very similar to what we have actually in the sun. Of course, the volatile elements have been lost, but those we know how much they are. And that then ends up with a very famous plot from 1956 from Harold Urey and Hans Suess about the cosmic abundances. And you see, this is all normalized to silicon at 10 to the 6. You see, of course, the overabundance of hydrogen and helium, and then for certain peaks in these abundances. And again, this is very similar to what we also find in the sun, where we can measure the elements. Now, what explains this trend in all of these abundances over 12 orders of magnitude? It's basically the shell model of the atoms that was started, obviously, already with Mendeleev. And so we actually have here the magic numbers, 2, 8, and 20, that are very peaks in abundances. Iron, very important element, the highest binding energy per nucleon. That's why it's such a peak there. And then you get a few other peaks that you see indicated over there. And so here we go from meteorites actually to nuclear physics. They tell us something about that. In fact, we can go one step further from nuclear physics to actually nucleosynthesis. And this goes back to a very famous paper from 1957, B²FH, it's called, as to how the various elements were formed. The burning of hydrogen and helium, basically leading to carbon, oxygen, nitrogen, neon, etc., makes the lowest elements. Then iron, already explained, that's a peak in terms of stability. And then beyond iron, we get into elements that are primarily made through neutron captures. That plays a large role in there. So this is what we can actually now also observe in space. This is a beautiful image made. It's a composition from data from the Chandra X-ray satellite and also the New Star satellite, a very recent satellite. It shows you the supernova remnant, Cassiopeia A. And what you see in the different colors is basically images in the X-ray lines or of these various elements. So silicon, magnesium, they all have their specific lines. Is in green. There you see them being produced. Iron you see being produced in large amounts, and then also here 44 titanium actually being produced in this particular case up to a fraction of % of a solar mass that is produced in this one supernova. So here we can see actually sort of element production in situ actually happening at this very time. Now, if you go beyond iron, then indeed the proposal was always that this would be done through neutrons, and that neutron-neutron star mergers would play a large role in it. A neutron star is one of the densest possible stars that you have, collapsing at the end of a stellar life, as much material of the sun in an area that is probably as big as St. Petersburg. So huge densities, and when they merge, that is actually where you have the conditions, lots of neutrons, in order to produce gold. And this was actually, this gold rush was actually confirmed just very recently when one of these neutron-neutron star mergers was actually detected by the gravitational waves from the LIGO-Virgo collaboration in 2017. Then they also took spectra of this event, and they saw the signatures of all of these elements beyond the iron peak that were actually produced here in this neutron-neutron star merger. So for this particular event produced several oceans in terms of mass of gold in just this one neutron-neutron star merger. Good. So that's a brief summary of how we make the elements in space. And again, if you want to hear more about it, please come to the symposium or look in detail at the poster that you see over there. I now want to switch more to chemistry. What can we actually do with these elements in space? Because space is actually very empty, it's very tenuous, it's very cold, and so chemists would expect that there is actually nothing happening there, that you just have the elements there. Moreover, we have this overabundance of hydrogen, this carbon, nitrogen, oxygen, the elements that we are actually interested in making organic molecules, for example, present at only a fraction of a promille. So, how do we go about, how and where do we actually go and search for molecules in space? Well, this is an image that may be familiar to some of you. It's the Orion Nebula that you can see on a clear night, also here from St. Petersburg. If you go to the sword of Orion, there's a little telescope, you can see the Orion Nebula. What you see here is this beautiful reddish glow, and that is, makes it so colorful, this nebula. But that's not the gas that we are interested in. That's actually the ionized gas, 10,000 degrees. That's too hot for molecules. We see here basically the H-alpha recombination line of atomic hydrogen. What we are interested in is these very dark regions that you see here. Oops, if you follow my, yep, there you can just see the pointer up there, these very dark regions on this optical image. And they are so dark because they contain these tiny little dust grains, little dust particles that actually absorb and scatter the light and make it look very dark. Now, this image also shows something else, namely the fact that this is not just a chemical factory, as we will see in a moment, but this is also actually a nursery of new stars that are being born at this very moment here in the Orion Nebula. That central part that you see over there contains thousands of young stars meaning only 1 million years old, not yet a few billion years old like our sun is. And in fact, it was Victor Ambartsumian, who I think was here at St. Petersburg State University and also at the Pulkova Observatory, that made this very important point. Up to the sort of 1950, people thought that stars were part of cosmology, that stars were there eternally. They did not think that stars could also be born and that stars could also die. And it was Victor Ambartsumian who made a very important conclusion, actually, by looking at a certain type of stars and looking at their distance from the clouds, like the Orion Nebula, that he said, you know, stars do not have eternal life. Just they also are born and they also die again. Oops, let me just go that, yeah. Yeah. So here we see these dark clouds, and if I now, this is down the Carina Nebula, this is a beautiful image from the Hubble Space Telescope. So this is in the light that we see with our own eyes. You see here these very dark regions, and if I would point my telescope, one of my telescopes, at these dark regions, that's where I would find a lot of molecules, and that's where I would also see new stars and planets being formed. And as I mentioned, these clouds are so dark because they contain these tiny little dust grains that you can think of as silicates or carbonaceous material. They are very small, only a fraction, a thousandth of a millimeter, a tenth of a micrometer, and they make up by mass about 1% of these clouds. So these clouds, one of these dark clouds that you see over here, is mostly hydrogen, molecular hydrogen, temperature very low, just above absolute zero, densities about 10,000 particles per cubic centimeter, which is much more empty than the best ultra-high vacuum that you have in a laboratory on Earth. It's mostly neutral. The ionization fraction is very low, maintained by cosmic rays, which penetrate into the cloud. Collision times are long, so we are not thinking of things that happen on a minute time scale, but we are thinking about collisions that happen maybe only once a month, and the time scale to reach chemical equilibrium may be of the order of 100,000 to 1 million years. So, for me, as originally also a chemist, for me this is really a unique physical and chemical laboratory in order to study chemical processes in an environment that's different from what we have here on Earth. So let's look at an example from elements to molecules. Water, of course, to hydrogen and oxygen. How simple can it be? Well, it turns out actually that the only way to make water is actually on the surfaces of these tiny little dust grains that you see over here. And this has been simulated, measured actually in laboratory experiments in various places, in Leiden, Paris, and in Japan. There's a hydrogen atom landing once a day on the surface of a grain. It finds maybe another hydrogen, goes off as H2. But it can also find an oxygen. Yeah, there it finds an oxygen. Two oxygens finding each other, making molecular oxygen. And then they make hydrogen peroxide, and then actually, yeah, there they make 2 water molecules. And so this is happening on the time scale maybe of a day, and now we fast forward to say 10,000, 100,000 years, and we make lots and lots more molecules of water, and then we make sort of this icy layer on the surface of the grains. And in fact, the bulk of the water that we have here on Earth, that is in your body, that is in the sea here around St. Petersburg, that water, the bonds between those water molecules were already formed 4.5 billion years ago in the cloud out of which our solar system collapsed. So think about that the next time you drink some water, that those water molecules are already 4.5 billion years ago. Of course, they have evaporated and recondensed again, but the initial bond was formed on these tiny dust grains that you see there. So as one of my colleagues put it, the water on Earth is actually older than the sun itself. Good. Well, we find not just water, we find lots of other molecules, surprisingly, under these conditions. If you look at the more diffuse clouds, we see carbon monoxide, we see H3+ there, simple molecules, but also already quite complex. Polycyclic aromatic hydrocarbons that we see there. If you go to the denser clouds, then the molecules are shielded from UV radiation, and we start to produce more complex species, like dimethyl ether that you see here, also these very long carbon chains. If you go to the accretion disks around young stars, then which planets are made, we're starting to probe the chemistry there. And then in comets, as we will see, is actually a very rich chemistry there. We see lots of molecules there that may or may not end up on a new planetary system. Of course, stars don't have eternal life. They will run out of material for nuclear fusion. When they do so, they will swell up, and they will actually return a lot of the elements that they created through nuclear fusion back into the interstellar medium. And that's when a whole new cycle of star and planet formation can occur again, now enriched with new elements that were formed there. We see also some interesting molecules, and that's under those conditions, such as, for example, fullerenes, the buckyballs. So we find specific molecules under specific conditions, which is nice also to have a diagnostic, not just of chemistry, but also a probe of the physics that is going on. Now, one of the big new astrochemistry machines that we have is actually the Atacama Large Millimeter Array. That is particularly well suited for observing molecules because we can look there at the pure rotational transitions of the molecule as they tumble end over end in interstellar space. And that is the first worldwide collaboration in astronomy between Europe, East Asia, and North America to put this large array actually on a high altitude plane in northern Chile. And just to give you an impression, in just 30 seconds of integration time, if you point at a high mass star forming region, you find all of these lines, all of these fingerprints of the molecules that we can uniquely identify with dimethyl ether, sulfur dioxide, acyl cyanide, etc., etc. And so basically each molecule has its unique barcode with which we can identify it in space. What have we discovered so far? Well, lots of simple molecules, lots of complex molecules. I showed you already some of them. Here we see a few other ones, such as this simple sugar, although not yet sugar in the chemical sense. Ethanol, there's actually quite a bit of alcohol in space. Probably the Orion Nebula has enough to fill 10 to the 27 bottles of whiskey, in case, or vodka, in case you're interested in that. But some of the prebiotic molecules, like the simplest amino acids, bases like purine and pyrimidine, they have not yet been found. And also this molecule that you see over here, which may not be necessary for the origin of life, but is certainly important for the maintenance of life, as we just sampled it, is not yet been detected. But what it shows is actually that these molecules are not that much more complex than the ones that we've seen already. So with ALMA, we can dig much deeper into searching for these complex molecules. Here you see some recent detections, tricarbon molecules such as isopropyl cyanide, and also the first chiral molecule here, propylene oxide, that has sort of a mirror symmetry here that you can see that has also been detected, although we cannot yet determine whether one of the two forms is enhanced or not. The large carbonaceous molecules that I mentioned already, especially the fullerenes, have been seen, and also very recently benzonitrile is sort of the first aromatic molecule that has been uniquely identified. The PAHs, we know that they are there as a class of molecules, but we cannot say whether it's coronine or one of the other PAHs that we are actually observing. Some of these molecules are actually frozen out on the grains, as we've seen in the case of water, and those are actually processes that we can also simulate then in a laboratory on Earth, and this certainly plays a very large role. Now, one of these clouds at some stage can actually start to collapse under its own weight, and then it will actually form a new star. And because the cloud always has a little bit of rotation, it forms automatically also a disk around the young star in which planets can then form. And so it's basically that gas and dust, that rich chemistry that we saw happening there, that is then transported to the disk and forms the basis for planetary systems. And thanks to ALMA, we also are going now into a new era of basically observational planet formation. So far, these disks look like little blobs, but now we can actually zoom into them and we can see sort of their structure and the locations in which new planets may be forming actually on solar system scales. And we can also now study the chemistry actually on solar system scales. Here are two young solar systems that are in the process of formation. And again, if we point ALMA at it, we see hundreds, thousands, in fact, more than 10,000 lines of various molecules, more than 100 different molecules, actually in this forming planetary system. And some of them are simple molecules, but some of them are indeed already getting to sort of prebiotic molecule, like the isocyanides, acetamide, etc. So we are now studying sort of the material really out of which new planetary systems are made. And how far can this complexity go? Well, you heard a lot about catalysis this morning. We are not doing catalysis in the sense that you are doing in terms of chemistry, that the surface plays a role, but the surface definitely plays a role in bringing the species together that can then react, starting here from carbon monoxide and hydrogen, that can form all of these sugars, in this particular example, going maybe all the way to ribose. And these are experiments actually done by one of our Russian PhD students in Leiden, Gleb Fedoseev. So this is very interesting to see sort of the chemical complexity that can happen actually on the surfaces of these tiny little dust grains in interstellar space. How do we then make planets? Well, in the simplest way, we just basically start from these tiny icy dust grains that we know already have quite a lot of material around them, and then we go to make planetesimals, planetary embryos, and eventually something that may or may not look like Earth. Now, comets are a very important intermediate step here. They are basically the building blocks of planets because that is sort of a size, kilometer size, that they start to interact with each other. And just recently, we had a fantastic mission, the Rosetta mission, that landed for the first time in humankind on the surface of a planet, of a comet. And it was actually a comet that was detected by two Russian astronomers, Churyumov and Gerasimenko, that you see over here. And so this is a mission that started already in 2004 and that encountered with the comet in 2014 and did wonderful observations there. And if you want to hear more about that, come again to our symposium where Maria Drozdowskaja will tell more about this comparison between comets and interstellar molecules. Perhaps the impact of these kind of comets actually brought the water and the organics onto Earth. We have some evidence from that, from the isotope ratios that we see actually in the water. And that could have actually delivered not just the water, but also organic material on Earth. So let me end here actually, and just give you a little bit of a glimpse of the future. What is the next frontier? We are now starting to discover exoplanets, planets around other stars than our sun. And more than 4,000 of them have already been discovered. And we know about the statistics that on average, every star has at least one planet. The next step is clearly to study the composition of the atmospheres of these planets and see whether they have signs of life there. This is an artist's impression of a star, our nearest neighbor star, Proxima Centauri, around which a planet has been detected, Proxima b. And with the next generation telescopes, here the European extremely large telescope, 39-meter telescope diameter, we will actually be able to search in the spectrum of that exoplanet for signs of life. What are we looking for then? Not just water, but probably a combination of both oxidizing and reducing materials, like water, oxygen, but also CH4, nitrous oxide, etc. Only the combination of them may be a sign of biomarkers. So I will leave you with this image, and to give you a little bit of perspective, this is an image that was taken quite some time ago by the Voyager mission, when it went just beyond Saturn. It looked back, and there it saw our Earth. That tiny little dot that you see over there. That's home, that's us. I think what astronomy does, it not only tells you where the elements came from, where we came from in terms of our Earth, in terms of the ingredients for the building blocks for life, but I think it also provides us a little bit of perspective and at the same time then also modesty and tolerance if we see that we are living on this tiny little dot in the middle of big galaxies. So, congratulations to UPAC from the International Astronomical Union with this symposium, with this International Year of the Periodic Table, with the 150 years of Mendeleev. And I'll leave you here with our motto for this year. We're all world citizens under the same sky. that you see over here, both in English and in Russian. And please follow all the events that we're having to celebrate this through our website. Thank you very much.